So, hello again. We'll start the practical class now. So we have the old assignments on polynomial computations. We'll finish it just in, I hope, quickly, and then we'll go to the P and P with the new assignment. So, okay. Could you please remind me which problems we did in class and which was left for home thinking? So, I think we did the first one, yeah, last time. Did we do the second one? I think yes, right? So this modeling of two-tape Turing machine. Let me quickly recall it. How do we model the two-tape machine and a one-tape machine, just without details? So if you have a two-tape machine, then you have actually two troubles with modeling on the one tape. So the first trouble is that you will have to keep pairs of symbols in a sense. So this can be done in two ways. So the first way is to just, so here is A and here is AI and here is BI. They are aligned one on top of each other. So one way of doing this, you are free of your internal alphabet. You can introduce arbitrary symbols. And you can introduce such compositional symbols like that. This will be just one symbol. And you populate your new tape with these two-layer symbols. And this will keep your memory. If you don't want this, so for example, if you want to get stuck on memory where you keep only zeros and ones, like on a real computer, what do you do then? You can just do interleaving. So you write A1, B1, A2, B2, etc. So this is one problem which we have solved, that two tapes are encoded into one. But the second thing, which is more important, is that you have to keep information about two operating heads. So a two-tape Turing machine has two pointers, on the tapes. And the pointers are not required to be aligned. They can go in different places. And therefore, you have to keep the pointer and also keep the state. And this is kept by adding it into the tape information. So you have these symbols. You can also have these Q first, AI, BI. Or even you can have Q first, Q second, AI, BI. Which means that you have both pointers at the same place and the states are Q1 and Q2. And here you have Q1 and the second point is somewhere else or something. So the second point is going to be Q2, AK, BJ. So this is with these layered symbols with interleaving. It's basically the same. You can say just that here you put Q1 before A2, for example, means that it looks like this. And somewhere here you have a NBN, and you just put here inside Q2, which is the state of the second one. And then what you are doing, when you emulate your two-tape Turing machine, each step is emulated as follows. So your real head of your one-tape machine is located before on the blank here. And the model is done like that. You have to, for example, you want to move the second pointer. You have to go to the right, find where this Q2 is located. Then you have to perform the step here, which means that you replace this Q2, you move it somehow. It's a local transformation which can be done by one-tape Turing machine in a constant number of steps. And then you go backwards and park your pointer at the beginning. This is important because if you don't park it, you don't know whether you should go to the left or to the right. Here you always go to the right, do your operation and go backward. And now the complexity is quadratic. Why? Because each step of the new machine requires the following number of steps. So if here you will have m elements, then each step is modeled by 2m plus some constant c, where c is the number of steps which is taken here. C is constant, it's just like 5 or something like that. And this should be multiplied by the time of the two-tape Turing machine, running time of two-tape Turing machine. And the next idea is that this m is less or equal than t2 plus the length of the input word. Why? Well, because I've just opened the chat for reading it. Just because the number of cells you could populate while running the Turing machine is not greater than its running time. And plus you will have also the length of the input word, which was originally in these cells. So this means that the running time is maximus quadratic with respect to this T2. Well, so we suppose that T2 is greater than the length of the input word. So this is the measure. This is how we model it. Okay, so 4.3, I think we discussed it several times, but okay. Does there exist a polynomial algorithm for satisfying DNF set? So just a question for you, just to remember what happened in previous classes.
Yes.
Yes, why?
Because to satisfy a DNF, it suffices to satisfy at least one clause. So we need to go through all clauses and see if there are any kind of controversies inside them.
Yeah, exactly. So how do we satisfy them? Let me write it down. So what is a DNF? So a DNF is a formula which is a big disjunction. Disjunction of some clauses. And DI is a conjunction. So it's, say, P1 and not P2 and something like that. So again, if you satisfy at least one of the clauses, you satisfy the whole DNF. So this means that you have to check them one by one. And once you say satisfiable, you are done. Because if you satisfy, say, D1, everything else doesn't matter. And how to check one clause for satisfiability? Well, the only case when it is not satisfiable, so not satisfiable, if you have this clause which is of the form something, 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 and Pj and not Pj. So this is a contradictory clause that cannot be satisfied. If there is no such contradiction, then the clause is satisfiable and the whole DNF is satisfiable.
But can we consider such a form to be normal if we have a pair of the same variable inside one clause?
Well, this is a good question. Formally speaking, it's not disallowed. Mm-hmm. So if you disallow that, what then happens? Suppose you have a non-satisfiable formula. What does it mean that the formula is non-satisfiable? It means that it is just constant false, yeah? And how do you represent the false constant as a DNF?
Constant false?
Yeah, if you have constant false in your language, then yes. You can also say that it is an empty DNF. And then your checking algorithm will be even easier. It just says if your DNF is empty, it's not satisfiable, it's non-empty, it includes at least one clause. If you have this notion of normality that your clauses should be, all the clauses should be non-contradictory, then if it's at least one clause, this clause is satisfiable, the whole DNF is satisfiable. But if you have neither constant false, nor you wish to use empty DNFs, then the only way to represent constant false is like this. But formally speaking, in the DNF it's allowed. Also in the CNF, you're allowed to have this. What does it mean? It usually means that this, so the clause is this or something, something. So if you have this clause in a CNF, it's just constant true, you can just remove it. Again, in a DNF, you can remove all the contradictory clauses, yielding an equivalent DNF. So it's an element of normalization, but the notion of normality in this DNF doesn't include this one. Okay, so these were easy ones. So did we do, so I think we did 5, yeah? We did Euler cycles, right? Yep. So I think last time we discussed this thoroughly. Yep. So we discussed that the Euler cycle exists if there is a specific criterion on the graph. So it should be connected and all things should be even. And we also discussed augmenting of cycles, right? We did this last time. Okay. And now let us discuss a point. Did we? I hope we discussed point 4 also. Yeah, or not? To check a graph being bipartite. No? Did we do this? I don't remember. Let us do it once more. So what's a this will be important because this will yield us to something for the next lecture. So what is a bipartite graph? So a bipartite graph is a graph which contains two parts and all the edges go between them. So you will have this first part, the second part, there are some vertices here, some vertices there, and all the edges can go only this way. There are no edges inside the parts. It is not required to be connected. There could be something else like this, for example, but it's bipartite. So in order to obtain an algorithm for checking whether the graph is bipartite, we'll introduce another notion that bipartite is the same as too colorable. So we are coloring vertices of our graph. So each vertex will receive a color. And here I drawn two colors, black and white, or red and green. Red and white. So a graph is called, the coloring is called correct or valid if vertices which are connected with an edge should be of different color. So if you have two vertices and they are connected, then this one should be black and this one should be white, or vice versa. But they cannot be both black, cannot be both white. This is a correct coloring. And of course, bipartiteness is the same as colorability. Why? Well, just because you can say that this is black and this is white. And the criterion of correctness of coloring is the same as the criterion that all the edges should go between parts. And vice versa. If you have a graph which is too colorable, we can say the black ones form one part and white ones form the other one. And all the edges will go between. So this colorability is the same as bipartite. So how to check whether a graph is too colorable? Polynomial. Well, let me, I think you have an answer, of course. Just
Can DFS be considered?
yes. For example, you can do DFS. You can go depth first search and try to color it. Just if you start with a vertex, you color it in black, then all its neighbors should be colored in white, and then so, yeah. So their neighbors should be colored to black. They could be like this, and etc. So this is depth first search. Why does it yield the correct coloring? Well, it's easy. If the graph is too colorable, then if it yields the correct coloring, if it doesn't come across a contradiction, then it will say okay. But what happens? Then this correct coloring. But what happens if the algorithm stops? So if it fails, it could fail. How can it fail? We are trying to color a vertex in. So suppose we are going. So we have colored this in black, black, black. And suppose we need to then do the next coloring. And what happens next? Suppose that, for example, these two are connected. What happens then? Then we have to color this vertex in white, but it's already traversed and colored in black. So why does this mean? So our algorithm is quite greedy. It just tries to propagate the coloring. But why does this show that the graph is not colorable, not too colorable? So our algorithm failed, but it doesn't mean that we don't have a coloring. Maybe another algorithm could take it.
Well, if we meet the vertex that has already been traversed and that is colored in the same color as we have colored the latest vertex, that means that there is a cycle that connects
And
the
the cycle is on.
latest vertex with the traversed one, and we can come to controversion when we take a look at the initial vertex.
Yes, exactly. So this vertex, suppose, let me make it a bit longer. So suppose that we did this, then we did this, then we did that, and then we returned here. So this means that we did a long way and we returned to a vertex we already traversed. So this vertex got traversed in two, so the depth, the level of depth, which, yeah, because of what cycle exactly that people are also answering in the chat. So we reached this in several steps. So here we did it in 2 steps. So this vertex was obtained at depth 2. And this vertex, the lower one, hope we can see it here. Here, the lower one is obtained in, I don't know, 1, 2, 3, 4, 4 steps. So these are both even. They can also be both odd, but they have the same parity. Why? Because the color is the same. The color is the parity. 0 is black, 1 is white, 2 is black, 3 is white, etc. So they have the same parity. Therefore, the sum of these green lines is even. And this is an extra one, which makes it odd. So the cycle will include 2 plus 4 plus 1, which is an odd number. And therefore, in our graph, we have an odd cycle. And if we have an odd cycle, then this graph cannot be two-colored or is not bipartite by the following consideration, that if you try to color this very cycle, not the whole graph, but only this cycle, you will actually fail, because you will have the odd number of vertices. They should be split into equal parts, which is not the case. So this is how it works. But just since we have some time today, today's problem sheet will be not that hard. Therefore, I will take an opportunity to show you another way of thinking about that, reducing this to another known problem. Suppose that we have, we have V. Okay, no, let me. So we're talking about two color, which is the same as being bipartite. So we have V, which is the set of vertices. Well, suppose we have n of them, as usual. And now let's introduce the following. These are going to be Boolean variables. We introduce Boolean variables for each point. And then we say the following. We say that P1 equals 1 if and only if Vi is white. So 1 stands for white, 0 stands for black. Maybe vice versa, it doesn't matter. And now we're going to write a formula phi, which says that it is a correct two-color. Well, by it I mean this assignment. So we have assigned some variables to our some values to our variables, sorry, and we want to know that this represents a correct coloring. How do we represent it? Well, for each edge, so there is an edge connecting Vi and Vj. For each edge, we should postulate that these guys have a different color. So what does this mean? What should we exclude? We should exclude them being both white. So this means that not Vi or not Vj. So they cannot be both white. At least one of them should be black. And dually, Vi or Vj, which means that they cannot be both white, both black. At least one of them should be white, right? Not V, P. Sorry, it should be P. The vertices are denoted by V's, and V's are the variables. So it's Pi, not Pi or not Pj, and Pi or Pj. And we write the formula, which is a big conjunction of all of that, for all Vi, Vj being edges of our graph. And this will be the formula of R. Now what happens? I think you already guessed what's going to happen next. Satisfiability of this formula is exactly the same as colorability of the graph, right? So if we satisfy the formula, we get values for P's, and these values are representing the colors. So we say that if this is true, then this is white. If this is false, then this is black. And this condition, which is expressed by this Boolean formula, is exactly the condition that this color is correct. Yeah. But this is not just a Boolean formula. What sort of Boolean formula is written here?
CNF.
It's not only a CNF, it's a 2 CNF. And for 2 CNFs, we have resolution, which is polynomial. So we just apply a resolution method, and this will give us satisfiability. And once we did satisfiability, we can find out a satisfying assignment. I think we discussed it, or we'll discuss next time. How to do it. I think we did this dichotomy, this how to get a satisfying assignment. The satisfying assignment will yield us a true coloring, and this true coloring will check bipartiteness of our graph. So this is how it can be done using Boolean logic. One can ask you what happens with 3 coloring. Well, with 3 coloring, you will have a 3 CNF. So with 3 coloring, you will have to introduce more values. And these, so for variables will be like that. You will have, for each vertex, you will have 3 variables, which says that this vertex is either red or green or blue. And there will be conditions like that each vertex has exactly 1 color. And this will be already a 3 CNF. And all these correctness conditions will also be represented by 3 clauses. And this will make it, well, it's still NP. Of a colorability question is NP. And it gets reduced to 3 sat, which is useless because 3 sat is NP hard. Actually, as we'll show in the next seminar class, it's 3 color is also NP hard because it's mutually encodable with 3 sat. But this is not a trivial fact. We'll discuss it next time. So this is the connection between graph coloring and satisfiability. So it looks like they're absolutely different, but they have actually they are equivalent. And you can also think about how to encode 2 sat in graph coloring into colors. This is not that easy, but it can be also. So then I like it for the following, that this is actually the usage of Boolean logic as logic. So what is logic in general? Logic is a way of mathematical, discrete expression of some facts about something, or real life or something, or graphs, for example. So usually people think that Boolean logic, or propositional logic, is too weak, that you have only atomic propositions and you have just Boolean logical connectors. You don't have quantifiers, as we discussed in one of the classes. You don't have modalities, you don't have description operations, roles and stuff like that. You have only variables and logical operations on them. And people think that this is just, maybe you can implement some, maybe logical programming, but you cannot implement real logic. You cannot talk about real objects. Here you can. So this is the exact formula that represents colorability in a really natural way. So we say that, okay, we have a graph and we represent elementary atomic propositions, which are PIs. They exactly represent the colors, and then we write a condition which is a logical one, and it is a condition of colorability. And this yields a polynomial time algorithm. For implementation, by the way, maybe even this is more convenient than writing DFS, unless you have it in a library. In network X, you will have it just as an internal routine. But this usage of resolution is also quite nice, effective, and this is just an example. Okay, so we still have point 6. I think we will postpone it until the end of today's seminar. If we don't have time, we'll do it next time. It's called so-called Hall theorem. Let's postpone it just in order to go to today's class. So these are quite easy, and let us just. So I don't want to give a big home task, because the next class will be the last one, and we'll have to do all the things in the class. Let us briefly look at the today's questions. So P and NP. All of this is conditional. The first problem starts with suppose that P equals NP. It's not equal yet. Okay, thank you. Yeah, so P is not equal to NP. This is a conjecture. We don't have to have a proof of that, but we believe in that in some case, to some extent. Okay, so let's do the first one. Let's think about them together. So suppose P is not equal to NP. Could there exist a polytime translation from CNF to DNF?
No.
Okay, does anyone else understand that the answer is no? How can we do this? So there is a CNF, and we try to translate it into a DNF. So it's generally possible. The problem is algorithmically solvable. You can just, for example, write down a truth table. Or you can use distributivity, and you can redistribute. Yep, you can open up the brackets and make your CNF a DNF. But each of these methods can lead to exponential blow-up. So the question to you, except you know the answer, is the following. Could this be done in polynomial time? So we know that the answer is negative. So how do we use these presupposition that P is not equal to NP? So, well, it should be a contraposition argument. Suppose we have a polynomial time algorithm that translates a CNF into an equivalent DNF. Suppose this is the case. What happens then? So we go by contraposition. Suppose we have a polynomial time algorithm which translates a CNF into an equivalent DNF. Yes. If you have such an algorithm, you can reduce satisfiability for CNF to satisfiability for DNF. And satisfiability for DNF is polynomially checkable. So if you have an algorithm, a polynomial, a fast algorithm, yeah, so that is not NP, that people ask, also saying in the chat. Exactly. So if you have such an algorithm, you can take CNF sat, which is the satisfiability problem for CNF. This is known by Zeitchen that it's NP hard. And then we will transform it into a satisfiability to DNF, and the satisfiability for DNF, as we discussed today, it is polynomial. So this means that in this case, CNF sat will be polynomial, but this means that P equals NP, because we have found a polynomial time solution for an NP hard problem. If P is not equal to NP, then this is not the case. So again, it's conditional result. We do not know by sure that the answer is negative. We know it only in the presupposition that P is not equal to NP. Okay, so the second is reducibility. Okay, let's postpone this for some time. You can just think about this and just try to digest what is written there. And let's go to 0.3. So let me comment on co-NP. So what is co-NP? Is the dual class, is the demonic NP. So let's recall what we mean by demonic. So suppose we have a decision problem. So a decision problem is some problem A, which A of x for each x returns 0 or 1. Right? That is this decision problem. So for each decision problem, we have a complement. A bar, which is 0 if A of x is 1, and 1 if A of x is 0. So the first observation is that if A is a polynomial decidable problem, then its complement is also polynomially decidable, right? Because, well, we'll just run the algorithm and then we do this swap of the results. This is trivial, it's nothing to say about this actually. But if you put NP here, you won't get NP. Why? Because the hint. So the hint is angelic and it's supposed for you to win, to return 1. But here is all the things are swapped. So you say that A of x equals 1 if and only if there exists a y such that R of xy equals 1. Well, and the size of y is less or equal than some polynomial. This doesn't matter. We think that the hint is always polynomial, but this is the existential quantity. Now, what does this mean that the negation, the dual of x is 1? It means that this is 0, it's not 1. So we have to negate this. And it's negated as follows. So for all y, such that it's polynomial, of course, you will have to have not R of xy, or the same as R of xy equals 0. Right? So this is demonic choice. The angelic choice says that there should be at least one hint which is given to you by the angel, which makes you win. But here the demon gives you the hint. So the demon wants to defeat you. And he betrays you and gives you the bad hint. That the hint is the worst hint you could ever suppose to have. And even for that worst hint, you should, so yeah, here it should be, no, it should be 1. Oh, it should be 0. The original R should be 0, or the same as the negation of R should be 1. So in order to win in this game, you should win with any possible hint the demon could provide you. And how this duality works in practice? Well, for example, the SAT problem is in NP, right? It's a non-deterministic polynomial. Because now the angel gives you the satisfying an assignment, and if this assignment is satisfiable, if that assignment is satisfying, then it will be okay. So if the formula is satisfiable, then the angel will give you the satisfying assignment and say, okay, use this and you will be fine. If the formula is not satisfiable, of course, the angel will not be able to give you the satisfying assignment. And in this case, it will, well, the angel will give you something, but you will fail. So it means that if you fail, it's not because the angel gave you the bad hint, it's because there's no good hint. The existential quantifier is falsified. So we have a dual problem, which is called tautology. So tautology is not polynomially solvable, well, unless p equals to b. It's a dual to SAT. How do you do with tautology? With tautology, you take I will say this is in Co-NP. Why? Because tautology can be solved by a non-deterministic polynomial algorithm with demonic choice. What does this mean? That the daemon, actually it's all the same. The daemon gives you an assignment, and you again just check whether it is satisfying. But with demonic choice, this becomes a solution for tautology. Because if the formula is not a tautology, then the daemon will give you the assignment which will fail you. We will give you that assignment that makes you fail. So this means that if the daemon cannot give you a bad assignment, then your formula is a tautology. So there's a funny thing. You have the same, very same algorithm, but with angelic choice, this non-deterministically solves SAT, and with demonic choice, non-deterministically solves tautology. Since we're on the positive side of the world, in this class, we're mostly discussing satisfiability. And this is the shadow part, where this is the demonic thing, but the algorithm is the same. And you can also develop the theory of co-NP completeness. It's absolutely the same. So you have the same reductions and stuff like that. They will all dual to co-NP and to NP, and NP hard, NP completeness is dual to co-NP.
Could you please define co-NP in a formal way?
Co-NP here is the same. So co-NP means that, so the problem is in co-NP, if there exists such a polynomially decidable function with two arguments, so we can say like that, that A is, so let's take the problem B. B is in co-NP if B of X is equals 1, if and only if, for all Y, such that Y is the polynomial of X, let's call it, let's call R prime of xy is R prime is the negation of this R. So it says the following, that for all y, for all hints of polynomial size, the result should be 1, should be true. Or in terms of non-deterministic computations. Again, you run you have a non-deterministic Turing machine. It's all the same as in NP, but the winning condition is different. So in NP, we said yes if at least one trajectory of the Turing machine yielded yes, right? Here, all the trajectories should yield yes. This is a co-NP class. Or another definition is as follows. You have the problem, you have its complement. If your problem is NP, then its complement is co-NP. So co-NPs are exactly complements of NPs.
So can we state that co-NP is a subset of NP?
No. It's dual, it's not a subset. It's dual, and here it says that they are different. So again, if you do NP, you have to win at one trajectory. If you do co-NP, you have to win at all trajectories.
Well, if the problem is in co-NP, that means that for any y, there is some function that is polynomially solvable.
No, the function is the same, it's fixed. That there is a function and it should be always true.
Always true.
While for NP, it should be somewhere true.
But doesn't that mean that for this problem there...
No, it doesn't.
But for any y, if this holds, that means that there exists y.
Yes, but this is not a decision question. So this means that, well, of course, it means that any particular, if you consider your problem as a set of positive answers, then the set for NP version is a superset of the set for co-NP version. But it's not a reduction. It's not a, so the question is not that you should win more times. The question is whether you can determine the winning. And well, what you said just now is that any tautology is satisfiable, basically. So if your formula is a tautology, then it's of course satisfiable, because it's true on all possible assignments, therefore it's true on some of them, right? But this doesn't help us. So if we know how to do this, it doesn't help us to do this. We have to go only by duality. Does it make things clear? So again, we're talking about a decision problem. Decision means that we have to decide whether it is 0 or 1. And if your problem, you can think about your problem as a set of inputs on which it returns 1. And for this set is going to be, of course, bigger for co-NP than for NP, because the universal quantifier is stronger than the existential. But your question is to answer whether it belongs there. So therefore, it's incomparable. Okay, so let's return to problem 3. So the problem 3 says that if NP is not equal to co-NP, then P is not equal to NP. It's problem number 3. Let's think about this for some minutes. So this means that in a good state, you will have the following. So the presumable picture, if all these complexity conjectures are true, is like this. So you will have this big class which is called NP. Inside this class you will have a subclass which is called P, and then you will have another class which goes like this, which is co-NP, and they're different. So here are NP complete problems, here are co-NP complete problems, and here we don't know. Is there a non-trivial intersection between NP and co-NP? Well, what is easy? The easy thing is that P is a subset of NP. We know that, right? Also, P is a subset of co-NP. Just because P is closed under complementation. You have a complement of a polynomial question, it's also polynomial. But we don't know that the intersection, or whether the intersection of NP and co-NP is the same as P. Well, this is just an open problem. We don't know anything. Okay, so, but let us show that if NP is not co-NP, that P is also not NP. How can we do this? This is an easy question, by the way. Well, the problem with this is actually it's formulated in a strange form. If you reformulate it in a better form, you will see that it is trivial. It's also good and logical. Где пересечение? Здесь нет пересечения. No, here we don't. This is another problem. I was talking about this one. If P and B is not equal to co-NP and P is not equal to NP, how can you reformulate this in order to make it easier to prove? What? I didn't hear. Well, the problem here is there's too many negations. It's hard to prove that P is not equal to NP, even under some assignments. How to prove that something is not equal? How can you reformulate these things in order to make it negation-free positive?
If P equals NP.
Yeah, this is the equivalent formulation is the following. If P equals NP, then NP equals co-NP. So these two formulations are just logically equivalent. They're the same, right? If A implies B, then not A implies not B, and vice versa. And not B implies not A, sorry, and vice versa. So this is called contraposition. Now I have to prove the second line. How do we prove it?
Isn't that pretty trivial?
It should be trivial, yeah, but we have to explain that.
If P equals to NP, then
Yeah, exactly. Because how can we show that? Well, let's for other people, let's make it a bit. I will remove the picture. It's nice, but it's too big, and I have to restrain myself to this central part of the whiteboard. So how do we prove that? We say that okay, what does it mean that P equals NP? Well, the interesting, of course, is that NP in this case includes P. The other one is well known. So this means that suppose we have A, which is in NP, then A is in P, right? A is a decision problem. Okay, suppose now that A belongs to co-NP. What does this mean? It means that the complement of A belongs to an NP, right? The complement problem. So this is the A bar belongs to NP. Then A bar belongs to P by this one. And then A belongs to P because polynomial class is closed under complementation, right? So in a polynomially solvable class, you will have complementations as you compute your polynomial function and just there to swap. And there is no quantifier which has to be flipped. So it will be the same P class. So this means that co-NP will also be a subclass of P. But that means that co-NP just coincides with P because P is always a subclass of co-NP. And this is the same as NP by our conjecture here. That's all. So the only trick in this question was to do this flipping. Okay. So now let's think about problem 4. I think we did something like that, but let's do it once more just for you to be more confident in it. So problem 4. Suppose set is in P, which is crazy, but suppose it's the case. And now we're trying to solve the search problem. To find out an algorithm which yields a satisfying assignment, just one. How can we implement such an algorithm? No? Any ideas? So suppose we can answer questions about whether something is satisfiable. And our question now is to get the assignment itself.
but it should not be polynomial.
No, it should be polynomial, of course. But we know that SAT is polynomial. We're now in the case where P equals NP. So any decision problem can be done in polynomial time, an NP decision problem. And now we're talking about the search problem.
Let's think about this.
So basically, we have to find the density.
Yes. No, it's an algorithm, as they say, with just a moment. I want to talk to other people also. Yeah. So we are. No, it's okay. At each class, there are some people who are more, say, I mean smart. They are more, say, coherent with the topic than other people. It's okay. There's nothing bad about it. I want just to talk about our people and maybe transmit some other ideas. So this is a conditional. 4a is a conditional problem. If you do not like conditional problems, look at 4b. But 4a is a conditional problem. We suppose that we have a polynomial algorithm for SAT. Well, as you know, this is highly unlikely because we suppose that p is not equal to np. And this will yield that p equals np. But we suppose that we have a polynomial algorithm for SAT. And this will tell us that how should I say? This will be an algorithm, as they say it with Oracle. So we can use inside, we want to implement a search algorithm for searching for satisfying assignments. And we can use the algorithm for checking satisfiability. So if you are crazy with these conditional ideas where you are required to use an algorithm which probably does not exist, look at 4b. It's actually the same, but in 4b, 2SAT is actually in P. So yeah, in really normal programming situation, you have this resolution method which checks your 2CNF for satisfiability. But formally speaking, resolution does not give you a satisfying assignment, right? Because what does resolution do? It saturates your CNF. It's a 2CNF that's all done polynomially. And then if the CNF gets saturated and you didn't come across the contradictory clause, the empty clause, then you will just say, okay, it's satisfied. But it doesn't give you a satisfying assignment. Now the question for B is how can you use this method in order to obtain the satisfying assignment, right? So a concrete one. This is 4b. 4a is the same, but it's imagination because you don't have really polynomial for SAT, but it's presupposed here. You can do 4b. Okay, so how can you do this? You know how to solve satisfiability, and you now have to find an assignment. The hint here is that you have to use your satisfying checker not once and for different forms. Let's think about this a minute.
Well, I have an idea, but I'm not sure about it.
Okay, great.
You can actually add your single variables to your formula, like if it's a CNF, you can add, let's say, and we have a variable A. We can add n A and check the satisfiability, and if it's still satisfiable, then A will be true. And
Okay.
if it's not, then you should add not A, and then this it would be satisfiable. So you would be able to, by adding those like single variable codes to your CNF and checking for satisfiability, you would be able to polynomially use the value for each variable.
Yes, exactly. This is the correct answer. So let me just tell it once more for all the public and also for the Zoomers. The answer is as follows. So we'll have the following thing. How do you guess your satisfying assignment? Well, the first thing, which is easy, first you have to check whether such an assignment exists. So you have a CNF phi. First you check it for satisfiability. So if it is not satisfiable, we are done. The search problem just says no, because if you don't have an assignment, you cannot yield it. So suppose that it is satisfiable. And you have variables which are P1, P2, etc., Pn. You have n variables inside your CNF. So what we do next? Next we say, okay, let's try phi and P1. Again, we check it for satisfiability. If it is satisfiable, then we can say that we can write that P1 equals 1. And now we have to find a satisfying assignment for this formula. Well, we do it recursively. Now we run our search algorithm, but we run it for a CNF where you have this one already processed. So if you so we're now trying to satisfy this, but if we satisfy it, then P1 will always be 1 because it's just postulated inside. So next you will try phi1, phi and phi1 and phi2 and try it. But what happens if this is not satisfiable? This means that this one is satisfiable. Why? Well, because the formula phi is satisfiable. We have already checked. If it is not satisfiable, just return that it is not satisfiable. But if it is satisfiable, then it has a satisfying assignment. And in such an assignment, there is a value for P1. It's either 0 or 1. If it is not 1, then it should be 0. So we added that. Now we check it for satisfiability. Actually, we don't have to check it for satisfiability because we know that it is satisfiable. Now again, we try phi and not phi1 and phi2. If it is satisfiable, okay, then phi1 is false, phi2 is true. If it is not satisfiable, then we have to put the negation of phi2. And this would, at each step, we check satisfiability. And finally, we obtain a CNF, which is known to be satisfiable, but which will include just one literal clause for each variable. So actually satisfying this formula can be done in only one way, by just putting the corresponding values to these variables. So if you have one variable clause, you can just satisfy it only. So what about running time? So how much time does it take us to satisfy it? Well, it's going to be the time we need for checking satisfiability multiplied by, well, n plus 1, I think, yeah? So this is the zeros check, and then for each variable you check satisfy, yeah? Okay, that's great. This means that if this is polynomial, then the whole size is also polynomial, because this n is a polynomial of the size of the CNF. And now we have this split. So if we're in the case A, where we have SAT, then all this stuff becomes conditional. We suppose that this is polynomial, then the whole thing is polynomial. But probably this is not polynomial, so everything gets void. And so this is a problem which is trivial. If p is not equal to np, then this presupposition is false. You get just x files of logic. And in 2SAT, you will have the same. The only thing you have to worry about is that your new formula will also be 2 CNFs.
but there will be two CNFs because you are adding only literals, and literals are clauses where the number of literals is less than 2. Therefore, this doesn't ruin the 2 CNFness of our formula. It's still a 2 CNF, and it's applicable for 2 SAT, and this is polynomial. It's by resolution, we know that. So in this case, it will be just a concrete polynomial, and the degree and the form of this polynomial, well, it can be computed. Maybe we didn't do it formally, but you can do it. You just have to calculate with what number of operations you need to implement 2 SAT. And we're done. So in point 4b, it works for 2 SAT, and now for 2 SAT, we have not only the decision procedure, which checks satisfiable, not satisfiable, but we also have a procedure which returns at least one satisfying assignment. Okay? So, and now we're going to go to 5a and 5b. So, what happens now? What sorts of problems for 2 CNF are decidable? So, let's see here. So 2 CNFs. First, of 2 SAT. It is first decision. So decide whether a 2 CNF is satisfiable. This belongs to P, right? We have just a second. Search. Well, it's also polynomial. Search means that you have to yield at least one assignment. It's polynomial. Well, I don't write that it belongs to P because it rather belongs to what they call FP, functional class, because it returns not a Boolean value, but it returns an object. Okay, so third, yield all satisfying assignments. How about that? We want to yield all of them. Can this be done in polynomial time?
No,
Why?
because there may be an exponential amount of satisfying assignments.
Yes, exactly. So suppose your CNF, it's stupid. So you'll be angry with me now, but sorry. Okay, no, so the stupid one is like this: P1 not P, P1 not P1, and P2 or not P2, etc. So this has a exponential number of satisfying assignments. Any assignment is a satisfying one. So in order to please the people who do not think that these are correct clauses in a CNF, I can make something more interesting. I don't know, like P1 or Q1 and P2 or Q2, etc. So these uses, in the end you will have something like Pn or Qn. So you will have 2n variables. And what is the number of satisfying assignments? Well, the number of satisfying assignments, I won't count it thoroughly, but it is greater or equal than 2 to the power of n. Why so? Well, suppose we made all the q's just true. We say that q is always true. This means that everything is already satisfied, and it doesn't matter how to what could you assign to p's. Ordinarily, you can assign units to p's, and then you can do arbitrary things for q's. But we will actually much more. It will, I think, 3 to the power of n. The correct answer is this. It will be 3 to the power of n. Why? Well, because for each pair of p and q, the only forbidden situation is 0, 0. Right? If at least one is unit, then it's okay. And this means that the number of, and what does this correspond, by the way, in the, so you can even add, you can, in order to make just 2 to the power of n, you can also add not p or not q. And this will correspond to coloring of a trivial bipartite graph. You just have p's, you have q's, and you just connect P1 to Q1, P2 to Q2, etc. It's a bipartite graph. And how can you color it? In each pair, you can color like that, or vice versa. This is 2 to the power 1. But if you have only this, you will have 3 because you can color them both in white, but not both in black. Okay, so this will give you an exponential number of satisfying assignments, for a non-trivial, by the way, to CNF. And therefore, there is no opportunity to make a polynomial algorithm which will yield all of them. And what we have to emphasize here is that this non-polynomiality is a very rare situation. This non-polynomiality is unconditional. So this is a situation, not the case where, okay, suppose that P is not equal to NP, blah, 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 then sat is not polynomial. This is non-polynomial just by design, because the result is not polynomial. So no condition, it's not conditional, no conjectures of complexity theory are needed here. Okay. So even for 2 CNF, the same for 3 CNF, by the way. It's also unconditionally non-polynomial in the yielding, in the total yielding drop. So now let's talk about 5b. And this is a more interesting one. As I said about polynomial delay, it's like Google, Yandex, it's like a search engine which should yield you all the answers which would satisfy you, but it cannot yield them at the same time because it could be a great amount of them. But it can yield them one by one. So it starts with a smaller one, and then it gives you next and next. How about such an algorithm for 2SAT?
Shall the same idea work here?
Well, that other people think also. I won't answer you now. The hint was that you have to use the same idea. So what is the idea? That you have to do dichotomy, you have to do this. But now you have to yield all the assignments. Yeah? Anyone else to think about this? People are tired. I see. Tired. But okay, so what should we do?
We need to go back every time when we finish the traversal of all
I
variables.
can implement this as a recursive call. It's recursively, it's more understandable. So we have a function phi. So if it is not satisfiable, then we're done, right? So what happens if it is satisfied? Then we check for phi and phi1. Again, if it is not satisfiable, then we just throw it away. But if it is satisfiable, then we're going to be recursive call for phi and phi1. Right? Next, we do phi and not phi1. Even if this is satisfiable, we also have to process this because now we have to yield all the assignments. And some assignments could be here. Again, if it is not satisfiable, then we just remove it. If it is satisfiable, then actually this check is actually not needed because we check both of these. If it is satisfiable, again, we do recursive call for phi and not phi1. Okay? So if it is not satisfiable, then both of these will fail, we'll just yield not satisfiability. But suppose it is satisfiable. What happens then? So it's either satisfiable by this or by this. So now we have to think what is first. We think how much time does this algorithm spend before the first answer. So if this is not satisfiable, what will happen? It will check this for satisfiability. And this is polynomial, right? And then it will recursively run this. And for this, we have this induction hypothesis that this will yield the first satisfying assignment in polynomial time. And then you will have to wait again for a polynomial time, it will yield the second one, and etc.
If this is satisfiable, then this will yield some satisfying assignments with polynomial delay. So it means that you will have to wait a polynomial amount of time for the first assignment, then again a polynomial amount of time for the second assignment, etc. And then it will stop, but then if this happens to be satisfiable, the same will happen here. This is induction. You will have to, we use our conjecture for a smaller number of variables. Because here you can just, this is true, then you can always remove the p's, and okay, you can do the following. If your p is in positive position, you just make your clause true, so you can remove it. If the p is negative, you have to remove the p from it, but keep the clause because it has to be satisfied by the other literal. Okay, and what is the base case on the bottom of this tree? Well, on the bottom of the tree, you will just have a formula which includes all the variables literally, and it's just satisfying. So using the depth of this tree is polynomial, is the number of variables basically. So this means that this algorithm runs with polynomial delay. Why is it so? That the whole tree is exponential, but we cleverly cut off the fruitless branches. So if we know that here is a branch with some assignments and all of these results here are zeros, this could potentially give us exponential time for waiting, because we have to check all of these, this exponential number of them. And this will wait and wait and wait without any result. But here there's going to be a formula which is phi and something, 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 which are the variables for the values for the variables we have already checked. And we know that it's not satisfiable, so we'll refuse to check this subtree. Every subtree we are going to check is fruitful, and at least one satisfying assignment. So therefore we remove the subtrees which do not give us satisfying assignments, and each waiting period is a polynomial in time. So if you write it as a timeline, you will remove this. So you start with the beginning of your algorithm. This is time. If there's no satisfying assignment, then the algorithm will just say no. It's just checking for satisfiability for 2c and f, which is polynomial. This can be done beforehand, just to to see whether there is something. If there is, then this is the point where you will get the first one. So this is alpha 1. Then you will get alpha 2. And go and get alpha mk, which is the last one. And then we'll think also for some time and say finished. So this time is t1, this is t2, here is tk, and this time is tm for finishing. So this is the time for the algorithm to conclude and say that there are no more satisfying assignments. This can be necessary for checking, for example, satisfiability of this guy. So each ti, where I is 1, 2, kf, each ti is that represent a polynomial of n, of the number of variables. Each of these times, but the k, so k can be exponential. K is also only bounded by 2 to the power of n, and this is the best possible bound because any assignment could be satisfied. So it's possible that this is a time. So the total running time is exponential, but the delays are polynomial, and we're allowed to stop at each step, saying, okay, we have enough assignments, we don't need more. So this is polynomial delay. So this is another type of problem, and it's polynomial delay. And finally, 4. So 4 is counting. How many assignments are there in the satisfying set? So how many, for given 2 set, how many assignments are satisfied? And this is called sharp two set, counting two set. So we're close to the end of today's class. So let's just check your intuition. How do you think about the counting problem? Is there a polynomial algorithm for that?
Probably no.
Well, of course, conditionally. But why? So your intuition is correct that all these methods of the dichotomy, they do not give us any idea how to count because, well, the only way to count is just to yield them all. But yielding can be exponential. On the other side, you cannot use the reasoning we used here to say that it's not polynomial, it's polydelay, but it's not polynomial. So here we just said, okay, the exponential number of them, and we cannot yield them all. But we can yield the number. The notation of the number, if even it can be big, it can be exponential, but the notation is small. So the answer can be given as an easy one, right? But but nevertheless, you are right. It's just, well, I will just formulate now. For this one, we will not prove it. On the next lecture, I will, so this is what they call sharp P complete. So it's easy to say that 3 sat, so easily 3 sat, well, it's sharp P complete. This is easy, well, just because if you even decision is hard, and counting, of course, is hard, right? But here decision is easy, and search is easy, and even yielding is polytime delay. But counting is hard. We will not prove this, we'll prove a related question on this hardness. We'll have to develop the theory of sharp P completeness. So the difference here is that you cannot refer to NP completeness because there is a gap. There is an example of problem which is P, but its sharp version, its counting version is sharp P complete. Next lecture will develop the theory of counting completeness and we'll show sharp P completeness for some problems and formulate exactly what does it mean for true set. But for the proof, I will refer to articles on that. So thank you. It's the end of this class.